All right, share screen. I hope this doesn't mess it up. All right, you guys seeing my screen okay? Oh, okay, cool. Okay, so tonight we're going to talk about unsaturated hydrocarbons, even though I kind of talked about them last week a little bit anyway. I lost my chat. Okay, I got it back up. So we're going to venture into more about this. So an unsaturated hydrocarbon is a hydrocarbon that has double or triple bonds. So here we have an alkene because there's a double bond here. It gets the ene ending. Remember, a saturated one is ane. This is ene. Here is a cycloalkene. This is actually benzene. I think we talked about that. If not, we'll do some more tonight. But again, you've got double bonds. And so that's an alkene. And then here you have alkynes. So here is an example of a carbon with a triple bond to another carbon. So this is an alkyne. And we've got a double bond and a triple bond, but you default to the largest bond. So this is going to be called an alkyne, and this becomes a functional group. And we'll see that in a minute. And we're supposed to be taking a break around 7-ish, okay? So double and triple bonds, bond length. I feel like we talked about this last week. Oh no, it's because I was reviewing it. Okay, good. All right, bond length. Single bonds are going to be longer than double bonds, and double bonds are going to be longer than triple bonds. And if you think about that, it kind of makes sense. If you think about it as like, two objects with rubber bands between them, and the more stronger it is, the more it's going to pull them together. So triple bonds are going to be very close to one another. Double bonds, not so much, and single are going to be your longest bonds between the atoms. The bond strength, however, is the opposite, which could be surprising. The triple bond is stronger than the double, which is stronger than the single. But the reactivity, I'm sorry, I said this wrong. The reactivity is the opposite. Double and triple bonds are more reactive than single bonds. But why is that? If triple bonds are stronger than single bonds, you would think that they would be less reactive, but they're actually more chemically reactive. And we're going to explore why that is. And to understand that, we have to look at molecular hybridization. I think you guys probably had this in your last class as well, so it might be a little bit of a review, but that's okay. Atomic orbitals will combine to make lower energy molecular orbitals, which then form bonds with other atoms. So when atoms come together and are forming a molecule, we have these atomic orbitals shifting into what are called molecular orbitals and then bonding together. Sigma bonds overlap end to end, like in the example here. This blue is a sigma bond between these two carbons. And so they are very strong. Pi bonds overlap edge to edge and are therefore weaker. So here you see a pi bond between what's actually happening is you can think of it as these two balloons are kind of bending into each other and merging. And so they're not end to end, they're more like, touching each other and so they're not going to be as strong as a sigma bond. Double and triple bonds are pi bonds. We'll see more of this in just a second. Also note that the sigma bonds with the carbon and the hydrogens as well. So this is our single bond here, single bond between carbon and hydrogen, another single bond with carbon and hydrogen. But this is the double bond, is a pi bond, and that's why it's not as strong as this end-to-end overlap. Any questions there at all? By the way, was going to put a extra slide in here about this, but I forgot to. All this stuff we're talking about, these are models of, it's like a way of describing a reality at the quantum level that's, you know, not really very easily understood. So, you know, the fact that we even talk about electrons being particles is kind of just a convenience. If you remember, light acts as both a particle and a wave. It gets really funky. So these are just attempts to try to describe a very complex reality. So, you know, you have to accept that for what it is. So here's some examples. In the case of ethane, we've got two carbons with single bonds all the way around. So these are going to be all sigma bonds. And so there's 7 sigma bonds here. 1, 2, 3, 4, 5, 6, 7. In the case of ethene, though, we've got a double bond here. This is going to be a sigma. This is going to be a sigma. This is a sigma. This is, and that one of those bonds between carbon-carbon is going to be a sigma. But this one here is a pi bond. Remember back here, here's the sigma. But now the double bond is going to be this pi bond between them. And so ethene has 5 sigma bonds and 1 pi bond. Any questions there? Everybody got that? Okay. Quiet bunch tonight. Okay, and then in the case of ethine, we've got a triple bond here between these two carbons. So there's 3 sigmas. There's 1 between this carbon and this hydrogen. There's 1 between this carbon and that carbon. And there's 1 between this carbon and that hydrogen. And these two are pi bonds. So we've got 3 sigma and 2 pi. And then I gave you just a little bit of a longer molecule here. So here we've got a CH3. We've got 2 carbons with a double bond between them, and then we got 2 carbons with triple bonds between them, and another CH at the end. So if you add these up, there's 13 sigmas. All these red bonds are sigmas. And then we've got 3 pi bonds, the 1 double bond here, and the 2 bonds that make up the triple bond between these 2 carbons. Okay, somebody asked, I'm sorry, you already explained this, but why is there a sigma and pi bond between the double and triple bonds? Why is there a sigma and pi bond between the double and triple bonds? Yeah, well, I think the next few slides might explain this. But if it doesn't, we can come back to it. But the way you worded it, why is there a sigma and pi bond between the double and triple bonds? Oh, okay. Yeah, because your first bond is going to always be this bond that's end to end between these 2 carbon atoms. And so this is what makes it a sigma bond, is that they overlap end to end. To make the triple bond, well, to make the double bond, let's say, you're going to have to bend these down together to make that second bond, which is a pi bond. And then really the third bond, you've got to have this other plane in here. So think of this Z plane coming in and out of the page. That's going to be your third bond, and they're going to be overlapping end to end as well. I think I have a slide that shows this, so, but let me know if it doesn't answer the question. We can come back to it. So when you have all single bonds with a carbon, this would be the case of this ethane, for example, you have what's called sp3 hybridization. And what this means is here's the normal ground state of a carbon atom. You've got 1s2, 2s2, 2p2, and this orbital is empty. Remember, p orbitals have 3 slots in the XYZ configuration, and your s orbitals always just have 1. And so this is the normal ground state. But what happens when this carbon goes to form a single bond, what it will do is it will kick one of these 2s electrons up into this pz orbital, and it will give you this. And so now you have 1 electron in the 2s and all 3 of these filled. And then they will combine. You'll take this 1 2s and these 3 2p orbitals, and you're going to make 4 sp3 orbitals. And these are at a lower energy than these p orbitals. Remember I said nature's lazy? So whenever it can form lower energy levels, then it's going to do that, and that's part of why this happens. And so what you're going to end up with is 4 electrons that can be shared, and this is why carbon shares 4 different electrons like this. And so there's 4 orbitals, molecular orbitals now. Hybrid orbitals or molecular orbitals, same difference. And they're going to be spaced out equally from one another. So the bond angle here is going to be 109.5 degrees, and this is called a tetrahedral shape. Tetra for 4, because you've got these 4 points on there. Does that make sense? I kind of went over that quickly. Any questions there? Lydia, you're talking. I don't know if you're muted or you're just kvetching or what. Actually, I don't think your mic's working because it doesn't show you muted. There you go. Now you're mute. Now it shows your mic. No, still can't hear you. Oh, you guys can hear? Oh, wow, that's weird. Can somebody else try to talk? Oh, man, I can't hear any of you. Why is that? Maybe it's on my end then. Oh, my speaker got muted somehow. All right, say something now, Lydia. Oh, no, I still can't hear you. Oh, boy, what's going on here? Oh, all right, try now.
Testing?
Yeah, I got you.
Okay.
All right.
I forgot my question.
Sorry.
No, so I guess regarding this, I was going to ask is, so anytime there's there's a bond, would you say that there is hybridization of carbon? Is that right?
Yeah, so you've got
Because
this.
you're sharing that electron.
Yeah, you've got this atomic carbon coming in here, and it's trying to bond, and so it goes through this hybridization process to form those 4 hybrid orbitals.
Okay, thank you.
Sure thing. All right. Oh, and this is the geometry of methane. So methane, you've got 1 carbon and 4 hydrogens. And so this carbon is sharing its sp3 electron with each of these hydrogens. Okay, when you have a double bond, this is called sp2 hybridization of the carbon atom. And so again, you have your carbon in the ground state with a 2p2 and the 2s2. And again, you're going to have this electron kick up. Let's see here. And it's going to form 3 sp2 orbitals. So this s is going to combine with 2 of these and make 3 sp2 orbitals. So it's the reason why it's called sp2 is it's 1 s orbital is combining with 2 p orbitals. And notice you still have 1 orbital that's not hybridized. And so what you're going to get here is you're going to get 3 sp2 orbitals, but you still have this p orbital left over with that electron in it. And this is what's going to form the double bond side to side. So it's going to combine here with something, combine here with something, here with something. Those are all going to be sigma bonds. But now this is going to have to bend down. And let's see if I give you an example here. Yeah. So here is ethane. So the carbon is going to form, here's its 3 sp2 orbitals. And this carbon has 3 sp2 orbitals as well. So this carbon is going to form a sigma bond with the hydrogen and a sigma bond with the hydrogen. And then it's going to form a sigma bond with this other carbon. And likewise here. And see, these are all end to end. These are all much stronger sigma bonds. These guys to form got to bend down to each other. And this is why it's the bond between the 2 carbons is stronger because it's got 2 bonds holding them together. But that pi bond is going to be more chemically reactive because it's strained. You know, if you think about like, what's a good analogy here? Like, pinching, like, what's a good analogy here, guys? Like, like really stiff tweezers or something was what I'm trying to think of, where, you have to really put pressure to bring them together. That's kind of what's happening with that remaining p orbital. And so by them bending down side to side, they're under more strain than these guys are. So the overall double bond between these two is going to be stronger than a single bond, but this bond's going to be more reactive because it's under stress. Does that make sense?
Can you put your example down really quick? So I printed off the notes and my notes look different than what you're showing here.
You probably grabbed it.
Follow along.
You probably grabbed it before I revised these slides.
Shoot. Okay.
Yeah, I wasn't really happy with my ones from before, and I found these, and I thought they were much better. But it should explain.
I'll reprint them.
Yeah, it should be the same. It's just this one's a little prettier than what I had. I think I had something hand drawn or something, didn't I? And so, yeah.
It's not as detailed as this. Like, I like this form better. It's easier to follow along.
Good. Yeah, that's what I was hoping, that it was better. So yeah, I review my slides every week, and if I see something that doesn't look very good, then I have to decide, am I gonna take the energy to fix it or just be lazy and leave it? So I've changed these. By the way, the bond angle for with a double with a SP2 hybridization is called trigonal because you now got a 3-point. Notice these are all in the same plane. These are kind of in that horizontal X plane. And so the bond angle here is going to be 120 degrees between these. The other thing I didn't say, and I apologize for this, I just realized this, is if you recall, s orbitals look like circles, but p orbitals look like this. So this guy in its normal configuration is going to be, the 1s is a circle. It's really irrelevant because it's a full shell, so it doesn't take part in the reaction at all. Your 2s is going to be a circle. And then your 2p's, that's the X, Y, and Z. Let me draw this for you real quick. Can I annotate this? Annotate. All right. So if you think about the planes, vertical didn't work out so well. But, you know, normally we think of this as X, Y, and the vertical here is Z. So p orbitals are, you've got one this way, and you've got one this way, and then you've got one on the x-axis like this. Is this ringing a bell from your last class? So that's the 3. This is actually one orbital right here, this and this. It's just the probability of that electron being above or below here is in that kind of a configuration, whereas your s orbital just looks like this. I don't know if that helped at all or not, but what these are really describing is they're electron clouds. It's the probability of that electron being in that orbital and one at any given moment in time. And again, like I said, this is at the quantum level, so even talking about these things as particles and all that is kind of more of a convenience, a convention than anything else. So that's why this leftover Z orbital looks like a p orbital, because that's exactly what it is. It's still a full p orbital, whereas these are these hybridized sp2 orbitals. Make sense? Now, how do I, oh, it's up here. Okay, clear all drawings. All right. Turn off annotates. Okay, cool. All right. And then finally, when you have a triple bond, you've got what's just an sp hybridization. So you've got your carbon in the normal ground state, and it's going to take and throw that one electron up there into that p orbital, but it's going to just take the 1 2p and the 1 2s and make 2 sp orbitals. And you're still now going to have 2 p orbitals left over. And so you're going to look like this. This is the image I was thinking of. So here you've got this sp orbitals here, but you still got your y orbital and your z orbital up there. And so these are going to merge together between the carbon and whatever it's bonding with. And these guys are going to be bonding with whatever it wants to bond with. This shape is linear because it's going to be all across this axis. And you can see here, this is a 180-degree bond angle between the two. And the example here is ethyne. So with ethyne, you've got two carbons, both sp hybridized. And so their hybrid orbitals are sigma bonds. They're both going to make a sigma bond with the hydrogen. And then now the p orbitals are going to lean into each other. So these two are going to merge, the green ones, and then the two purple ones are going to merge and form your third bond. But you can see that you've got the second bond, this third bond are both that side-to-side pi bond, which is going to be more chemically reactive than this much more stable sigma bond here. Does that make sense? So again, those two carbons are going to be really held together because there's 3 rubber bands holding them together instead of 1. But it's going to be more chemically reactive than just a carbon-carbon because you've got these strained bonds that are in the pi bond formation. Any questions there? Yeah, this is on the test. Could be on the test. I believe there is a question about this on the test. Can I give an example? Boy, it's been so long since I've looked at the test. I haven't reviewed it yet. It'll probably be, like I said, I don't make really hard tests for you guys. So it'll probably show you like, let me go back here. It'll probably show you like something like this and then say how many sigma bonds and how many pi bonds are there. Or it might say, what's the hybridization with these two carbons here, right? So this is going to be sp because it's a triple bond. It's going to be something like that, not too complicated. Any other questions along these lines here? All right, that was the toughest part of the evening as far as like technical stuff. We are at 7 o'clock, so let's take let's come back at 7:15. So you got a 13-minute break, and then we will resume and continue working on the chapter. So break time, yay. Are people coming back? Okay, well, it's hard to tell when nobody has cameras on. Looks like a couple of you maybe are back. But we will continue. So we're going to talk about the naming of alkenes and alkynes. So rule number 1 is the "-ene" suffix. We're going to replace the "-ane" with "-ene." Very simple. Rule number 2 is you're still going to choose your longest chain that has the double bond in it. So in this case, you could go 1, 2, 3, 4, 5, 6, but the double bond isn't in that chain. So you're going to want to pick this one instead. So this has 1, 2, 3, 4, 5. So this is going to be a pentene, not a hexene, because the double bond wouldn't be in the main chain if you went this way. Make sense? And then again, you're going to start numbering your carbons, but you're going to start closest to the double bond. And in this example, we're going to start at this end since the double bond's right there. And you're going to get 1, 2, 3, 4, 5, with this being your ethyl functional group hanging off of the chain. And you're going to use the lowest number carbon in the double bond to indicate where the double bond is at. So in this case, we've got a pentene, and this is called 2-pentene because the second carbon participates in this double bond. You wouldn't call it 3-pentene, you go with the lower number here. If you have multiple double bonds, then you add di, tri, tetra, so forth and so on to the end of the name. So in this case, we've got 2 double bonds, and it's 5 carbon chain. So this is going to be a pentadiene. And now you name the first double bond is on the second carbon here, so that's 2. And the second double bond is on the 4th carbon, or starts with the 4th carbon, so that's going to be 4. So this is 2,4-pentadiene. And then if you have a substituent hanging off of this chain like I've got here, again, you're going to have, you're going to name your functional group first, and that's going to be on the 3rd carbon. By the way, this is numbered. And so this will be 3-methyl, and then 1 and 4-pentadiene, because the 4th carbon and the 1st carbon are the ones that begin the double bonds. Does that make sense? Any questions there? A little joke, before the organic exam you look like this, but after it you've got 2 double bonds, so I'm diene. Okay. If you don't have anything on a ring, then again, you don't have to put the 1 in there. This is just simply cyclohexene. So it really doesn't matter where the double bond is at. I'm glad you like the joke. Okay. Now, if you have substituted cyclohexenes, if there's only one double bond, then you number the carbons as 1 and 2, and then you number the functional group with the lowest number that you can get. So here we've got the double bond, so we're going to make this number 1, number 2 around the bond, and then you're going to have 3, 4, so this is going to be 4-methyl cyclohexene. If you have more than one double bond, then you're going to give one pair a 1 and a 2, and then the second pair the lowest possible numbers. So in this case, we've got 1 and 2 carbon, and then now 3 and 4. You wouldn't go this way. You wouldn't go, well, I'm not even sure how you do that. But anyway, you're going to name 3 and 4, and then that means this 5th carbon, and this is the 6th carbon, so this 5th one has a chlorine in it. So that's going to be 5-chloral, and then 1,3-cyclohexadiene. Any questions there?
What happens if it's a triple bond?
We'll get to those. Those are coming up. So here's a practice one for you to do. Take a few minutes. How would you name this compound? Okay, Kayla's got a suggestion. I'll let other people chime in. Now remember, you got to number your double bond. So it can't just be 2-ethylbutene. Yeah, looks like we have a consensus here. This is 2-ethyl-1-butene. Notice in this particular example, you can go either way. You could go 1, 2, 3, 4, or you could go 1, 2, 3, 4. Both of these, no matter which way you count them in this particular case, you end up with 2-ethyl-1-butene. So that's just, you could count them either way with that given example.
I thought you said to go for like the straightest chain if you have.
The longest chain, not the straightest,
Okay.
that has the double bond in it. So in this particular case, it works either way. It's just, circumstantial coincidence. Yeah, but yeah, don't think longest or straightest chain, think longest chain that has the double bond in it.
Yeah, no, I think I was specifically talking about when both have the exact same number of carbons.
Both of what? Both, like if this had two more here or something?
No, both. So like, right, like you're saying you can go 1, 2, 3, 4 and go turn and go down, or you can go 1, 2, 3, 4 and go straight.
Yeah.
Since they both have 4, I thought you were supposed to go straight.
Oh, it actually doesn't matter.
Okay.
Straight doesn't really matter. Just you want to go with the longest chain that gives you the lowest numbers, and with the double bond in it. So if it happens to be straight, that's fine, but it doesn't really matter. This is just sort of circumstantial. Ooh, what was that? All right, how about this one? You've got 2 double bonds. This double bond is especially reactive because it's kind of squiggly. That's a joke. So how would you name this one? And remember, this is a methyl group hanging off here on this end. Alicia, is it Alicia or Alicia, or I'm not sure I pronounce your name.
Alicia.
Alicia. All right, so Alicia's got one up. Aaron's got one up. Wait for a couple more. All right, looks like we got a consensus going. Hey, nobody typed flower row. So yes, so you're going to go with 1, 2, 3, 4. So that gives us our 1,3 cyclohexadiene. And then that means this has got to be 5 and this has got to be 6. Good. There are some common names. This is ethene. It's also commonly called ethylene. And this is propene. This is 1-propene, but it often gets called just propylene. So sometimes you'll see that. I don't believe that I test you guys on common names, but I can't 100% promise that, but I don't think I do. But this is just more, I'm thinking in terms of you guys encountering these names in the real world. And I want you to kind of be aware that there are these common names out there. And so if you have a carbon, a single carbon with a double bond, remember this was a methyl group. Well, this now gets called a methylene group if it's a double bond. And with an ethene as a functional group on something, so you got 2 carbons with a double bond. This is a common name. It's called vinyl. And we're going to see this in a bit with polyvinyl chloride, PVC. So vinyl just means it's an ethene functional group. And this is a very common, you see this a lot. This one, not so common, but a propene group is called an allyl. So again, just want you guys to be aware of those things. So here's an example. This will often get called methylene cyclopentane. Or this is what, yeah, this often gets called methylene cyclopentane. we would call this methyladine cyclopentane. Vinyl chloride, we would call this chloroethene, but a common name is vinyl chloride. And we would call this 3-bromopropene. Actually, that's wrong. This should be 3-bromo-1-propene. Sorry about that. But sometimes you'll see it called allyl bromide. All right, our line angle formulas that you get used as shorthand, it just draws the double bond in there as just an extra line in the thing. So here, if we look for our longest chain with the double bond in it, we can go 1, 2, 3, 4, 5, 6. So this is a hexene. It's a 1-hexene since that double bond's on that first carbon there. And then that means this is 3,5-dimethyl because you got the 2 methyl groups hanging off of there. And in this case, it's a diene because we've got 2 double bonds. Our longest chain is pretty obvious, 1, 2, 3, 4, 5. And so this is going to be 1 and then 4 pentadiene. Again, notice you could start on either direction on this one as well. It doesn't matter. So this could be 1, and this would still be the 4th carbon. So this is 1,4-pentadiene. Here, the longest chain with the double bond in it is going to be 1, 2, 3, 4, 5. So that makes this a pentene. And that double bond's on that very first carbon, so it's 1 pentene. And then that means we're going to have on the second carbon an ethyl group here. So that's 2 ethyl. And then we've got 3 methyl for this methyl group here. So 2 ethyl, 3 methyl, 1 pentene. And then again here we've got another diene. So we've got 1, 2, 3, 4. So this becomes 1, 3 butadiene. And then that, it looks like I counted it. So I got to count from this end because that gives this methyl a smaller number. So if we go 1, 2, 3, 4, then this becomes 1, 3 butadiene, and this is 2 methyl because it's on that second carbon. Notice if I came this way, it would make it 3 methyl, and that makes it larger. So that's why we started at this end. Does that make sense?
Wait, why is the one above it 1 pentene?
Because the largest chain with the double bond is 1, 2, 3, 4, 5. So that makes it pent, right? And that double bond is on that very first carbon, so that's going to be 1 pentene. Does that make sense? This is your functional group, and this is a functional group. If you went this way, it'd just be 1, 2, 3, 4. So you can get a longer chain going this way. Oops. Get a longer chain going that way. Cool.
But if you start counting it from the 1, isn't that 4? How do you count that?
This would be 1. Remember, you start at the double bond, so this would be 1.
Got it, yeah.
Okay. All right. Isomers with alkenes. So you have constitutional isomers and alkenes. They can be positional, where the double bond is in a different place. And then they can be skeletal, where the arrangement of the carbons is different. And then you also could have stereoisomers, which we looked at last week briefly. So positional isomers is like this. This is 1-butene because the double bond is on the end of the chain. And this is 2-butene because the double bond's in the middle. So these two have the exact same molecular formula, but they are isomers of one another because of where the double bond is at. And it's its position in the chain. That's why it's called a positional isomer. Skeletal isomers is when the structure changes. So in this case, we have 2-butene. You've got 1, 2, 3, 4 with the double bond on the second carbon. So this is 2-butene. But in this case, the longest chain with the double bond is a propyl. So this is propene. And the methyl group then becomes a functional group off of that. So this is 2-methyl, 1-propene. I think the reason why I don't have the 1 in here now that I think about it is I believe that you don't have to say the 1 if it's a 1. I'm pretty sure the book says that as well. So I don't think I'm screwing that up. I think it's you don't have to put the 1 in there. It's implied. But anyway, this is 2-methylpropene. But again, same molecular formula. It's just structurally different now. It's not just a change in where the double bond is at. It's actually the structure's different. And these two are therefore isomers of one another. Any questions there?
Is all this going to be on the test?
Yep. And then stereoisomers, we've already talked about. You have cis and trans. So these methyl groups are on the same side of this double bond. So this is going to be cis-2-butene. And then here the methyl groups are on opposite sides of the double bond. If you draw a line down the middle, you see that they're on opposite sides of each other. So this is trans-2-butene. So these two are stereoisomers of one another. And then if you look at dienes, you end up with, did I animate this? I guess not. Okay. So here we have 1, 2, 3, 4, 5, 6, 7. So that whole chain has got both double bonds in it. So that's going to make it a heptadiene. And then we've got it's 2, 4, because this is on the second carbon and the double bond, and this double bond is on the fourth carbon. So it's 2, 4 heptadiene. And then it's trans-trans, and this is why I got the different colors. Because if you look at it, this double bond, if you draw a line through here, you've got an ethyl group on this side, and you've got this whole thing out here on that side. So these are in a trans configuration. They're on opposite sides of that double bond. Does everybody see that? So that's the green circles. But now if you look at this one, you've got to determine whether this one's cis or trans. So you draw a line through the middle, and I've got a methyl group here, and then I've got this whole thing on this side. So again, this is in a trans configuration as well. And so this becomes trans-trans-2, 4 heptadiene. Any questions there with that? If we took the same compound, but we just flipped this ethyl group here with the hydrogen on either side, you now end up with a trans-cis configuration, because if we draw the line through here, now you can see that this whole beast, this whole green circle, is on the same side of that double bond as this ethyl group here, and therefore this is in a cis configuration, but it's still a trans on this one. So you draw a line through this double bond, you've got a methyl group over here, and then you got this whole thing on this side, and so this is in a trans configuration. So this is trans 2,4-heptadiene, but this is trans cis 2,4-heptadiene. And these are isomers of one another. These are stereoisomers. Any questions there? I get the feeling people are freaking out a little bit or something. You'll be fine. All right, so we looked at trans-trans and trans-cis. What would cis-cis 2,4-heptadiene look like? Try to draw that out and just tell me when you're done. Not going to expect you to try to post a picture up in there. Do you want me to put it back to this other one so you guys can reference it? So you want to do a cis-cis here. Alrighty, looks like people are finishing it up. And so here is your cis-cis. I drew it in a stick structure. But again, if you draw a line through this, you now have this ethyl group is on the same side as this whole beast. So this is a cis. And then on this side, you got the methyl group down here. And this whole thing, yeah, maybe, oh, I did draw circles. I knew I had circles appearing somewhere. So these guys are in cis configuration as well. They're on the same side of that double bond. And then if you look at this double bond, you've got this whole thing there and this whole thing there. That's cis as well. So that gives you the cis-cis. So all we did was rotate this end here. Go back here. We just rotated this down and this up, and that gave us this configuration. By the way, this is actually why you have stereoisomers with double and triple bonds, but not with saturated bonds where they're all single. If you have all single bonds in here, the difference is with a single bond, this group, so pretend this is a single bond between these two carbons, this CH3 and this hydrogen can freely rotate around that single bond. And so you can get the CH3 being on the top or the bottom. But once you get a double or triple bond in here, this can't rotate anymore. And so it's being held more strongly in place. And so this can't change. And that's what makes the isomers cis and trans. Does that make sense? Yes, this lecture will be posted. I will get it up tomorrow. You mean the recording of the lecture? The slides are already up for you to look at. But yes, I'm recording and I'll get it up on YouTube in the morning. Okay, let's go beyond this. I'm not sure what this is. Was this another problem, or maybe I was just showing you I think I was just showing you the other version, right? So here we have trans-trans, we have trans-cis, cis-cis, but then you can have, cis-trans. So this would be the other stereoisomer in this set. So here, this is a cis, because this guy's on the same side as this guy. Did I draw circles again? No, I guess not. Okay, so this is a cis, because this methyl group is on the same side of the double bond as all of this stuff. And this one here, though, is a trans, because this ethyl group is on the opposite side of this double bond with this all over here. So this is our last stereoisomer in that set. So you have trans-trans, you've got cis-cis, then you've got trans-cis, and then cis-trans. Does that make sense? So that's all your possible combinations there. All right, chemical reactions with alkenes. How are we doing on time? Okay. So just like with alkanes, you can burn alkenes. You can combust them. And again, you're going to react it with oxygen, and you're going to get carbon dioxide and water, as any other combustion process is in place. So this can happen here. Addition reactions, what you're going to have happen here is this double bond. Remember, this is a pi bond here, and that's more reactive. That's going to pop if you react it with the right substituents. A and B here is just placeholders, like X, kind of a thing. And what you're going to get is you're going to get a single bond between these two carbons, and you're going to get an A on one of the carbons and the B on the other. Does that make sense? So that sigma bond's going to stay in place. That's a stronger bond. But this pi bond's going to pop and break, and then the carbon will form bonds with these two substituents. And this is the case with hydrogenization. So hydrogenation, you've got the A and B is just two hydrogen molecules. So you've got propene here, 1, 2, 3. So this is propene, double bond. React it with hydrogen, and the catalyst is heat and a metal like a nickel or platinum. And that pi bond's going to pop, and you're going to get a hydrogen on this side and a hydrogen on that side, and this gives you propane again. So you can convert propene into propane by just reacting it with hydrogen. Any questions there? You can also do this with halogens. So in this case, it's chlorine. You've got 2 butene. In the case of halogens, though, you don't need a catalyst or heat because these guys are so reactive. And so here I've got 2 butene, 1, 2, 3, 4. And it will react with this chlorine, and it will give you 2,4-dichlorobutane. Because again, that pi bond's going to pop, and you're going to get your 2 chlorines attaching to either side of that former double bond. So 2,4-dichlorobutane, not ene anymore, because there's no double bond. So watch that on the exam too. Make sure your enes and anes and ines are there. Any questions there?
What was the
What's that?
hydrogenic one?
Hydrogenation.
Oh, yeah, I'm
So
sorry.
this is the two hydrogens. This is the exact,
What does it react with to get propane?
pardon me,
What does it react with to get propane and nitrogen?
the hydrogens here. This is just your catalyst,
Okay,
a heat and a metal. I'm not going to ask you on the test, like, tell me what catalyst to use or something. You're not going to get that.
okay.
But you need a catalyst in the case of hydrogenation, but you don't need it in halogenation. You don't need a catalyst or heat, either one, to do that reaction. And then you could do hydrohalogenation. So here you take an acid like hydrogen chloride, and I've got ethene, and again, you're going to pop that pi bond, and you're going to end up with a hydrogen on one side and a chlorine on the other, and that's going to give you chloroethane. So we're going from ethene to ethane because it's not a double bond anymore, and it's chloro because this is just a methyl group here, right? So you've just got the one chlorine, and so this is called hydrohalogenation because you've got a hydrogen and a halogen. And this could be HBr, this could be HF, it could be HI, but with any of the halogens.
Do we need a catalyst for hydrohalogenation?
No, again, it's kind of a mouthful, isn't it? Again, these halogens are so reactive that you don't need catalysts.
Thank you.
Go back to the hydrogenation slide.
This one?
Yeah, this one, thank you.
You just wanted to meditate on it for a second?
Yeah, something like that.
Okay, you can also hydrate alkenes. So we're going to add water to it. And you have to have acid to do this. It's the catalyst. In this case, it's sulfuric acid. And so you got this, in this case, it's ethene. It's going to react with water, and you're going to pop that pi bond again. And you're going to add a hydrogen on one side, but an OH group on the other side. And voila, you've made an alcohol. This alcohol is a chain with an OH group on it. And this is everybody's favorite alcohol, ethanol. Active ingredient of all your favorite beverages, if you partake. You can actually create ethanol from ethene by hydrating it. These all are essentially the same reaction, as you can see. Any questions there?
So all of these reactions are going from a single bond to a double, I'm sorry, from a double to a single, so you're going from enes to anes?
Yep,
on all of these?
you're popping that double bond. That's that pi bond that's stressed, right? They're leaning into each other instead of being end to end. And so it's going to pop, and then the carbons will bond with the substituents here. So this is going to come apart, and this is going to come apart, and you're going to get the bonds like that.
So will we get a formula, and will you ask us what is this? Is this hydration, or is this hydrogenation, or like what is the important thing for us to pick up on how to distinguish which is which?
What you might get is a question like, what's the product of these two things? So I'll give you all of this all the way over. I'll give you the reactants and the catalyst, and then you have to tell me what what the product is, or I might ask you just to name the product. So you might have to look at it, figure out what it's going to break down to, and then how to name it. Right? So if this was propene, then this would become propanol.
Okay, thank you.
Okay, so what would react with bromine? So this is a halogenation reaction to give you this. So this is a this is a 1,2-dibromocyclohexane, right? Somebody say something? So what are you going to react with that? Kayla says cyclohexene. Everybody, what do you think? Is she right, wrong? Not sure. Any other thoughts? Okay. Yep, you guys are right. So, isn't that cool? I covered up the little question mark. And again, in this particular case, it doesn't matter where you draw the double bond. But yes, this is going to be cyclohexene. So this double bond's going to pop, and you're going to add a bromine to either side of that bond. Okay. You could create polymers by doing this. And so this is how they make polymers. There's all kinds of polymers out there. Polymers are used in plastics. They're used in the medical field. They're used to make films, you know, like your ceramic wraps, nylons, like, you know, I'm sure none of you wear nylons anymore, but, you know, back in the day, it was very popular. That was one of the early polymers that was invented or discovered, was nylon, and it was made into women's pantyhose. That's where the term nylon comes from. It's a brand name. But anyway, so what you're going to do here is you're going to take a chloroethene and you're going to react it. You're going to do a hydrohalogenation to this. And so what you're going to end up with is you're going to end up with the hydrogen attaching to one side of this bond. And it's not going to attach the chlorine here. And instead, it's going to attach a whole nother one of these. So you see these two are identical. I know my drawing's not the greatest, but I tried making them different colors so you'll see how this grows. So that double bond pops. You're going to get the hydrogen on this side. So you've got a CH3 CHCl. And instead of it reacting with the chloride ion here, like we normally would do, instead this carbon attaches to this carbon. And this is another methyl group, and this is another CHCl. And so it combines like this. And so you now have CCCl with another CCCl. So it's like a symmetrical little pair. But then this reaction, if you use excess hydrochloric acid, this reaction can continue, and now it adds in another one of these guys. And so now you end up with your original double bond connecting to this, and then it connects to yet another one. So what's happening here, I better make this clear, is this got formed just like this did. It reacted with a hydrochloric acid and popped that double bond. So if we think about this, where'd my ink pen go? right? Let me annotate here again. Got to find my controls. Where are they all at? They're spread across 3 monitors. So draw here. Okay. All right. So this guy. Ooh, I don't like that. That's like a highlighter or something. I was trying to get it not so skinny. All right, let's try that. All right. So this guy got formed by this same reaction. So you're going to have this C double bond C Cl reacted with HCl, just like this one, and produce this. And there's going to be a free chloride ion flying around as well. So that's where this guy came from. And the same with this guy. This is coming from that same reaction as well. Everybody see that? So what's happening is in the presence of excess hydrochloric acid, you can get this happening, this chain building up, and instead of it doing a full substitution reaction. And this can go on and on and on in the right conditions. We're not going to worry about what those conditions are. Let me go back to my mouse. So what you'll end up with is a CH3 CHCl. That's one of these guys here, And then you're going to have a CH2 CHCl n times. This is the letter N, meaning any number of times as it connects in here. And then on the other end, you're going to have another CH2 CHClCl. This will end the reaction, because instead of bonding yet again, it's now going to pick up this chloride ion and end this polymerization. And this N can literally be hundreds of these guys repeating over and over again. See that? This is just shorthand for that, saying this chain can be in here hundreds and hundreds of times. And if you recall, we said a common name for ethene is vinyl. This gets called vinyl chloride. It's a common name for this. And because it's now this huge molecule with potentially hundreds of these repeating substituents, it gets called polyvinyl chloride. And this is abbreviated PVC. Anybody know what PVC is? You can find it at your local store. It's also in your house.
It's like your pipes.
Yeah, it's plastic. It's a hard plastic. It's not the only plastic. It's a kind of plastic. Like I said, polymers get made. Contact lenses are made out of polymers. What do you call it? Cellophane or whatever, the stuff you put over your dishes, the see-through stuff, saran wrap, that's a polymer. When they put on, they have fake skin for burns, that's a polymer that's got active water. It's got water sites on it, so it hydrates the burn and helps it heal better. Polymers come in all shapes, sizes, and they can be very flexible like saran wrap, but they can also be very hard in the case of polyvinyl chloride. And that's why if you go to the store, like that white pipe is PVC pipe, and that's a thick, hard pipe. So Michelle asked if PVC is the generic term of all links. Yes, all links of this particular compound. So this is, if you were using something else, then it wouldn't be called PVC anymore. It'd have another name. But this is this reaction can happen very quickly. You guys ever seen a polymer reaction happen? It's pretty cool. There was actually I saw a video of this. If you Google it, you'll probably find it. There was a contestant for like Miss America or Miss Universe or something, where her like what's the word, talent was chemistry. She had like a PhD in biochemistry or something, and so she did this reaction of a polymer where it just like she poured the stuff and it just shot straight up in the sky and made this huge column of this like foam like stuff. And it can happen that quickly. If you Google that, I'm sure you'll find that it's pretty cool. Just how visual it is, it just blowing up like that. So are all polymers considered plastics? I don't believe so. I'd have to double check that, but this is just one example. So you're doing the hydrohalogenation, but you're driving it to form this with lots of excess hydrochloric acid, and it will form these long chains and make this, in this case, a hard plastic. Oh, I need to clear my drawings. Okay. Let's try to, it's 8:07. Let's try to do alkynes because this is pretty straightforward, very similar, if I remember correctly. The naming rules for alkynes, remember again, this is a triple bond. So it's the same as alkenes, except you're going to change the ene to an ine. So this is 3-methyl-1-butene. Your longest chain with the triple bond in it is 4. So this is 3-methyl-1-butene. In this case, you've got 1, 2, 3, 4, 5, 6, 7. So this is a heptine. Don't get fooled here. There's 3 bonds here in this kind of notation. There's the 1 sigma bond between the carbons here, and then here's your other 2 pi bonds. So that's a triple bond there. So that's 3 heptine. And then you've got a methyl group on both sides of this 6 carbon. So that's going to be 6,6 dimethyl 3-heptine. Any questions there? Again, common names. We would call this ethine. It's frequently called acetylene. You guys probably have heard of acetylene torches that are used in welding. It's using that common name for that. It's actually just ethine gas that you're burning. And then here's the case of like a dimethylacetylene. So it's taken the acetylene part and then just saying there's 2 methyl groups on it. So sometimes you'll see names like this as well. All right, so here's a triple bond, and it's got an iodine here and a chlorine here. So how would you name that? Everybody take a crack at that one. I put all this work into a little extra project for you guys. I don't think we're going to need it. I think we're going to fill up our time. You're home? Nope. Look at the video. I popped the headlight. The case Of course. All right. What you guys got here? All right. So we've what we have here is we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. And again, you want a number closest to the triple bond. So this is going to be 1, 2, 3, 4 no name. What did you guys got? All right, most looks like we got a bit of a mixed bag. So that's 4 no name. And then that means that this is going to be 5, 6 chloral, because that's chloral is higher in the alphabet than the iodo. And then 7, 8 iodo, no 9. Does everybody see that? So 6 chloral, 8 iodo. That's how it is for triple specifically. Why is it a straight line? Oh, yeah, this is just the way that they draw the notation. You have to realize that that means there's a carbon here and a carbon there. It's the same with double bonds as well. Yeah, it's a linear bond as well. Okay, alkynes have isomers as well. They cannot have stereoisomers. You don't have cis and trans isomers around triple bonds because there are no up and down positions. There's nothing, because you've got 3 of the 4 bonds taken up between these carbons. There's no way you can have like an up on one side and down on the other. It's linear. So you don't have cis and trans isomers on alkynes. You can have positional and skeletal isomers. So here is a positional one, the triple bonds at the very beginning of the chain. So that's 1 hexyne. And then here it's in the middle of the chain. So this is 3 hexyne. So these are positional isomers of one another. And then here we can have skeletal. This is 1 pentyne. And then here you've got 3 methyl 1 butyne. And these guys are skeletal isomers of one another. Any questions there? Okay. Physical properties of alkynes. They are going to be soluble in organic solvents as well. They're going to be less dense than water. Their boiling points will increase the bigger that they get. And smaller alkynes are gases and larger alkynes are liquids. So your acetylene is a gas, but something like a nonine is going to be a liquid. Chemical properties. The reactions are similar to alkenes, except that the triple bond can react with both constituents to go all the way to an alkane. So here we have hydrogenation. You've got a triple bond here. You've got propyne, and it's going to react. And one of these pi bonds is going to pop, and you're going to end up with propene. That's just like, well, I guess it's not the same. But then this reaction can continue if you have enough hydrogen, and you can pop that second bond and end up with propane. So if you have enough hydrogen, you can go from a alkyne all the way back to an alkane. That make sense? Any questions there? All right, aromatic hydrocarbons. So an aromatic hydrocarbon is an unsaturated hydrocarbon. I don't think this is exactly correct. Unsaturated hydrocarbons that contain a 6-carbon ring is benzene. I'm saying that it has to have 6 in the ring to be considered aromatic. I'm gonna have to check that, guys. Anna's drawn on my screen. I'll come back to that. I have to think about that a minute. But this is benzene. You've got 3 double bonds within that ring of a 6-membered ring. This often gets drawn as just a circle in the middle of it. And sometimes it even gets drawn this way, just a circle with a slash through it. At least that's the way we used to do it in undergrad. I don't know if that's like a thing, but it's a notation that we used. Here are some examples. Here's a benzene ring with a methyl group hanging off of it. This is called toluene. If you've got, here is a benzene ring with 3 nitrite, and NO2s is nitrite, and also a methyl group. This is trinitrotoluene, because you've got these 3 nitrite groups on a toluene. And this is abbreviated TNT, which you may be familiar with. This is used sometimes in explosives. Aspirin is a case of an aromatic compound. You've got a benzene ring here, and it's got this CO2H, and then a carbon with a double bond with the oxygen, and another oxygen connecting into the ring with the methyl group off the end. So aspirin is actually an aromatic compound. Furan is a common name of a 5-membered ring with 3 double bonds in there with an oxygen in the place of one of the carbons. This is nasty stuff. It really reeks and is very toxic. Naphthalene is 2 benzene rings fused together. Does anybody know what naphthalene is? Another common household thing, at least back in the older days. Your grandma may have naphthalene in her closet or in a storage chest. Yes, they're called aromatics because they have an odor to them. Mothballs, correct. Yep. Mothballs is naphthalene. Pyridine, another very nasty aromatic compound. It's a benzene ring, but one of the carbons has a nitrogen in place of it. And I used to work with this a lot when I was working in the lab, and my wife always complained because I would come home smelling, no matter how careful I was. She'd be like, "You're messing with all these, nasty stuff." Yes, these are all aromatic compounds. Here's ethyl benzene. You've got this ethyl group hanging off of a benzene ring. A benzene ring with an OH group off of it. So this is an alcohol. Is called phenol. And you can also get what are called fused rings. So here you've got a benzene ring that has a 5-membered ring fused onto it. And we'll see much more of this when we get into the biochemistry side. A lot of very complicated molecules have these kind of fused rings like this. Oh, and here's our history highlights. So everybody always thinks of TNT being in dynamite. This is actually a little image that's used in the game Minecraft. I had to put a video game thing in there. But the reality is dynamite doesn't have TNT in it. It has the trinitroglycerin. This is TNT here. This is explosive, but it takes a lot to actually get it to explode. TNT was actually invented, and it was 30 years before they realized it had explosive properties. What's in dynamite is nitroglycerin. This is the formula for nitroglycerin. Remember, you're not getting tested on any of this, just a little make Izzy happy moment. But this is nitroglycerin. That is the very explosive compound that is used in dynamite. Alfred Nobel created dynamite, and it was so dangerous that there were many explosions of this. One of them blew up his factory and killed his younger brother. And he was so horrified that he created this very destructive item that's why he created the Nobel Prize. So he took his millions that he earned and established the Nobel Prize system with some of his money. Here's a picture of Alfred over here. He was a Swedish chemist. And nitroglycerin is also used to treat angina, which is chest pains. And they're very small pills, and they're kept usually like in a little container like this on a keychain or a necklace. My dad had angina when he was older, and he had one of these around his neck and could pop one if he was having an angina attack. So it treats heart problems, but in large doses it becomes dynamite. All right, so naming rules of aromatic hydrocarbons. Again, because you have the 3 double bonds in here, this just gets treated as one thing, benzene. And so this becomes chlorobenzene. Here you've got an ethyl group off of it, so this is ethyl benzene. And now we're back to that iso thing again. You've got 1, 2, 3 carbons, a chain attached to a benzene ring. So this gets called isopropylbenzene. Here we've got a benzene ring with 2 chlorines on it. So this is going to be 1,2-dichlorobenzene. And here we've got 3 bromines. And it doesn't matter where you start. So you just got 1, 2, 4 tribromobenzene. And then here we've got, now it does matter because you've got the differentiation between bromo and chloro. So this is going to be 1 bromo and then 3, 5 dichlorobenzene. Any questions there? So try to name this sucker here. I tried Minecraft. I couldn't really get into it. I don't know why. I think it'd be more fun if you were playing with other people. It just kind of felt lonely to me for some reason. Okay, answers are rolling in. Looks like we're building a consensus. So yes, you have 1 bromo, and then go this way, 3 chloral, and then 5 ethyl benzene. This is your ethyl group hanging off the end there. Oh, and we're at the end, and it's 8:30. So I did go back in chapter 1 and put problems on both. And I did the same thing here. Somebody said they had a 6th edition. I think that'll match 7th edition. We may run into, I looked it over and I didn't see any with this chapter. I think this is chapter 13 in the 7th edition book, whereas this is chapter 2 in the 4th edition. Except there is a 4th edition that's got extra chapters in it. And so that's 13 as well, if you have that one. But we may run into some naming convention differences. I looked them over and I think we're okay. But if we run into something that's really puzzling, let me know. Yeah, your practice problems are like your study guide. If you can do these problems, you can check your answers in the back. If you're doing well on those, you're going to do fine on the exam. So let's talk about the exam for a few minutes. So it will go live Saturday morning, unless you guys want Friday afternoon. I think last term, some people were wanting to take it on Friday, and I'm fine with that. If you guys want, I could have it be available like in the at noon on Friday and go to midnight on Sunday. Because sometimes people work the weekends and they don't have time off. Do you guys want that or don't care? Either way. Okay, so yeah, I'll kick it off on Friday at noon then. And then once you start it, you've got 90 minutes to take the test. And then, like I said, when it's done, you'll be able to see your grade right away. And yes, you could take it till midnight on Sunday. It will end at midnight. And don't wait till right before midnight because it will shut off and you won't be able to finish the test. So
I just want to let you know, I looked in the book and you were correct. The 6th edition, or the 6th edition that I have is chapter 13 for the unsaturated and then chapter 12 for the saturated.
Okay, yeah, it doesn't look
Just
like
in
he,
case anybody else has the book too.
yeah, thanks. Yeah, it doesn't look like he changed the problems or anything between the editions. I actually have a 4th edition. Remember I said somebody gave me a PDF of it? It's the full-blown one. It looks like that matches as well. And so, um, yeah, so you could see there's not a ton of problems here. Like I said, my tests are pretty straightforward. I'm not trying to trick you. I'm not going to give you uber complicated things. It will test you on the material, so you need to know what a hydrohalogenation reaction looks like and, things like that. But it's all multiple choice or matching, true or false, or sometimes there's like reordering. So you might get like single, double, triple bonds, put them in order of shortest to longest or something like that. Or single, double, triple, put them in order of most reactive, things like that. So there could be some ordering. But there's no math, there's no drawing anything or short answers or anything like that. And like I said last week, if there's data you need to answer a question, I give it to you in the problem. That doesn't happen so much in these first couple of chapters, but that will be relevant more later. So I did put together an exercise. If you guys want to do it, we do have another 25 minutes. Let's try it. Let's see what happens. Because this is going to be a little different. So what I'm going to do is just curious how this will work. And this will be good practice. So these are just more practice problems. But what I want to do is, here, let me get out of the slides. I have a Google Jamboard here. So I'm going to put the link in the chat. So I got to change this to anyone with the link can view. Oh no, I need you to be able to edit it. Okay. And don't wipe out the questions though, please, because I'd like to reuse this if it works okay. So I'm going to put this in the chat to everybody so you can get to it. And then what I was going to do is I'm going to put you guys in breakout rooms for 10 minutes. And you can try to do the problems. So this Jamboard, let me open it up here and show you. This Jamboard, there's 8 boards. So I'm going to make 8 rooms. If you're in room 1, you'll do this one. There's 2 compounds here to name. If you're in room 2, you'll do the second one. And there's a couple to name, so forth and so on. Make sense? So you'll have partners to work with and you guys can talk to each other. And there is, some of these do have drawing, and there's tools over here that you can draw with as well. This is do the best that you can with it. Right here is a pen to do drawings on it as well. And if you want to type in the names, you can do a text box, or you can just write it out if you want to do that as well. Sound cool? This is an experiment. We'll see how it goes. I wanted to try this. Any questions before we go? And once you're done, you can come back. It's set up so that you can come back into the main room once you're done with your couple problems. So I'll give you about 10 minutes, and then I'll bring everybody back, whether you're done or not, and then we can kind of go over them. So let me see here. Breakout rooms, here we go. So I'm gonna make 8 of these and put you guys in them all automatically. And here we go. All right, so remember room 1 does the first one, room 2, the second, so forth and so on. All right, did you guys get an invite to go in? Should have. It looks like a few people got rooms by themselves. Are you okay with that, or you want me to move you into another room?
I can move into another room.
We can move you into 7 if I can figure out how to do it.
Okay.
Alrighty. Are you done, Julia, or were you in there by yourself?
I was in there by myself, but then I got kicked out.
Oh no.
So,
Do you want me to toss you in one of the other rooms?
Sure.
Guess it doesn't matter. Everybody's got 2 except you, so I'll throw you into room 1. I can figure out how to do it. Oh, you're up here as unassigned. There we go. All right, there you go.